Okay, next exercise 62. So in this one we are given a finite field F having n elements, and we have to prove that for any non-zero element x in F, x to the power n minus 1 is equal to the unity 1 in the field. Actually this one is very easy, almost immediate, if we recall a result from group theory. Since the set of all non-zero elements in the field is a group of order n minus 1 under multiplication, it follows from the fourth corollary to Lagrange's theorem from group theory, which is theorem 7.1, that for any element x in this multiplicative group, that means any non-zero element in F, we have this, and that's it. So what this corollary says is this: if G is a finite group, and x is an element in G, then this power of x, where the exponent is the order of G, is equal to the identity element of the group. It's that result. So in this case our group is the multiplicative group of all non-zero elements in the field. Because the field has n elements, the order of this group is n minus 1. So now you can see how this is true. Next. Let F be a field of prime characteristic. Prime characteristic P. We know that every field either has some prime characteristic or it has characteristic 0. In fact, every integral domain has this property, and fields are also integral domain. P, where P is some prime. Prove that this following set, the set of all x in F such that the pth power of x is equal to x, is a subfield of F. So we can just simply apply the subfield test on this K that we have come across in exercise 29. But at the same time, we will also have to apply another result of an exercise which lets us say something about such fields of characteristic P. and that one is this. Okay, but before we do anything, we have to make sure that K is a non-empty subset of F, because otherwise you cannot conclude anything about K. Note that since the pth power of the zero element in F is equal to 0, we have 0 in K. So that means K has something, it's not the empty set. Now we can apply the subfield test. We are not explicitly going to say that from exercise 29 we are getting the subfield test. It has a name and that's just it. So what we do, we choose two elements in K. What does the subfield test demand? It demands that x plus y should be in K, minus x should be in K, and also xy should be in K. Well, we do not see these three things in the actual subfield test, but in place of showing that x plus y and minus x both belong to K, you can at once also show that x minus y belongs to K. However, we will show that those three elements belong to K because that is a little easier. Then the pth power of x is x and the pth power of y is y. That is just coming from the definition of K. Now, by the result of exercise 49, actually part A of 49, but in exercise 49 you have what we are now going to use. By exercise 49 we have this thing. You may recall, in fact you go back to exercise 49, there you will see that we have already proved this. But now this is nothing but x and that power is y. So the pth power of x plus y is also x plus y. So x plus y belongs to K. Then what is the pth power of minus x? Well, minus x can also be thought of as minus 1 times x, because we are in a field which after all is a ring, and when a ring has a unity, then minus x becomes equal to minus 1 times x. This is one of the ring properties. But now multiplication in a field is commutative, because of which this pth power is just the product of these two pth powers. Okay, the pth power of x becomes x, but what to do with the pth power of minus 1, that we have to see separately. It of course depends on whether p is even or odd, and accordingly it will be plus 1 or minus 1. Since p is a prime, we can have p even, and that there is only one such case, p equal to 2. If p is equal to 2, then this is nothing but x. Okay, but we do not want this to be x, we want this to be minus x. so that the pth power of minus x becomes minus x. However, when p is 2, then the characteristic of the field is 2, and in such a field, every element is its own additive inverse. And why is that so? That is because 2x is equal to 0. Characteristic is 2. So in this case, this power becomes minus x. On the other hand, if p is odd, here we have it more quickly. Then this is just simply minus x. So, in any case, this is equal to minus x. Hence, minus x also belongs to k. Finally, we see the pth power of the product xy. Again, because multiplication is commutative, it is equal to this, which is just simply xy. So, xy belongs to k. Thus, by the subfield test, well, because it's a name of a test, you can make it capital if you want. By the subfield test, k is a subfield of f. So that's how we have the solution. Next. Yeah, this one is very interesting. Suppose that A and B belong to a finite field, a field of order 8. We have already shown that any finite field must have a prime power order. So 8 is a legitimate order. No finite field can have, say, for example, order 12, because that is not a power of a prime. To a field of order 8, and that a square plus ab plus b square is equal to 0. Prove that a is equal to 0 and b is equal to 0, not or but and. So that means both a and b must then be equal to 0. And also do the same when the field has order 2 to the power n. With n odd, and this order 8 falls, I mean it satisfies those conditions because 8 is 2 cube where that exponent 3 is odd. So instead of just solving this one, let us solve the general case. Then automatically this one will also come under that. Let f be a field of order 2 to the power n where n is odd and let a and b belong to f that satisfy these conditions. Then you know one formula from elementary algebra. This is equal to a minus b times a square plus ab plus b square. How are we able to use this formula which we know from elementary algebra in this very general setting of a field? That's because when you derive this formula by carrying out the multiplication, all you are using are the field properties of the field of real numbers. You are not using anything special about real numbers that is they are real. Nothing special about that number system is used to verify this thing. And for the same reason, this identity is valid also in the field of complex numbers or in the field of rational numbers. So all we are using are just the field properties. So in a general field also this should be true, and it is true, but this is given to be 0. So this becomes 0, i.e. a cube is equal to b cube. Now our aim is to show that a and b are both 0. Now let's see what happens if we suppose that a is non-zero. Say, if we suppose a is not equal to 0, then you can divide on both sides by a cube because the field is an integral domain. So non-zeroness of a implies that a cube is also non-zero. Or c cube is this is not 0, of course, this is 1. C cube is equal to 1 where C is just a name given to this element B over A or BA inverse. Now can C itself be 0? Of course it cannot be 0, because if C is 0, then you have 0 equal to 1, which is not possible in a field. In a field, 0 is never equal to 1. Or not since C is not equal to 0, which means that C belongs to this subset, which we already know is a group under multiplication. And looking at this equation, can you say something about C as a group element in this group? Its cube is equal to the identity element. So, from the theory of orders of group elements, when they are finite, we have this, that is, the order of C is either equal to 1 or it is equal to 3, because from this equation we know that the order of C, whatever it is, has to divide the exponent 3. And this is a group under multiplication. Let's just mention that. Is a group under multiplication. So, from C cube equal to 1, we have order of C equal to 1, i.e., which just simply means having C itself equal to 1, or order of C equal to 3. Okay. So either C is equal to 1 or C has order 1 or C has order 3. Now suppose C is not equal to 1, that means C is not the unity in the field, then the order of C is equal to 3. But now we use one of the corollaries to Lagrange's theorem, which says that the order of any group element in a finite group has to divide the order of the group. Now, what is the order of this group? I do not remember which corollary this is of Lagrange's theorem, so I just simply write the result. And so, by that corollary, what I have just now described, 3 has to divide the order of this multiplicative group, which is, you know how many elements F has. F has 2 to the power n elements, from which we have removed 0. So, this. But is this possible? Since recall that it was given that n is odd. Since n is odd, n is equal to 2m plus 1 for some non-negative integer m. And we have these congruences. I mean, we can just simply rephrase divisibility or lack of divisibility in terms of congruence or incongruence. And in these congruences, we are going to consider the modulus as 3. This is congruent to since 4 is congruent to 1 mod 3, so we can replace 4 with 1, and 2 is incongruent to 0 modulo 3. So 3 actually cannot divide this 2 to the power n minus, this is incongruent to 1, because then only we can say from these congruences that 3 actually does not divide 2 to the power n minus 1. No, not 0 here. And 2 is of course incongruent to 1 mod 3, because 2 minus 1 is not divisible by 3. 2 minus 1 is 1 and 3 is 3, and 3 is a prime, it cannot divide 1. This contradiction I think I need ink, more ink. This contradiction means something has gone wrong. What is that thing? Always, whenever something like this goes wrong, it is the latest supposition that is wrong, that is the last supposition. And what is the last supposition? What was it? For us, it was the supposition that C is not equal to 1. That means C has to be equal to 1. Proves that our last supposition is wrong, or we can just simply write this, that C must be equal to 1. But then if C is 1, then B cube must be equal to, well, previously also we had B cube equal to A cube. Oh, C is not, C is not cube, no? C is just simply B over A. So B must be equal to A. But do not forget that we are still under a supposition, that first supposition. So according to that thing, so now what can we do with this new information? We can apply it to the given hypothesis that A square plus AB plus B square is equal to 0. So how many A squares we will get? 3 A squares. But because the field has order 2 to the power n, and we know that in such a case the field must have characteristic 2, so we can just simply write in place of 3 square 3a square minus 2a square, because minus 2a square will be 0. A square is equal to 3a square minus 2a square, which is equal to a square. So that means a square is equal to 0. And again, since we are in a field, so this implies a must be equal to 0, and this is a contradiction. If you want to make this place more clear, you can write within parentheses that since f has order 2 to the power n, the characteristic of f is 2. And I think, if I am remembering correctly, this in fact is exercise 35 in this set of exercises itself. You go and see exercise 35. that justifies this step, namely the characteristic is actually equal to f. Thus, and what is it that is being contradicted? Namely, our supposition that a is not equal to 0. That's where we started everything, with that supposition. But in spite of supposing that, we are still getting a equal to 0. That means a not equal to 0, supposition cannot be true. So actually a has to be equal to 0. This is false. So a must be 0, and because of this equality, b must also be equal to 0. Oh, just hold on. No, we cannot use a equal to b here, because this condition is something that we have obtained as a result of those suppositions, and one by one we have proved that all the suppositions are wrong, and that is why we have just simply managed to show that a is equal to 0. Now if you redo all these things from using not the supposition a not equal to 0 but instead b not equal to 0, then doing all the similar things, you will also end up concluding that b is equal to 0. That's how b is equal to 0, not because of this. So you can see that we can very easily get confused. You are supposing things, and in the hope of proving that those suppositions are wrong, on the way, if you find any such condition, you should forget about that. You should only see the final conclusion. Okay. We do not know anything else about a, only that a is 0, and that's it. Similarly, one can prove that b is equal to 0. So that means we have got what we wanted in the general case itself. So it also subsumes the case of order 8 within itself, and that's it. That is the solution. And finally, let's see one more. (65). Let f be a field of characteristic 2. So it's here it's given that f has characteristic 2. With more than 2 elements. So that means already any field must have at least 2 elements, and they are the 0 element and the unity. But it's given that our f has at least another one. At least 3 elements. Well, more than 2 elements, but at least 3 elements, same thing. The meaning is same. Show that x plus y whole cube is not equal to x cube plus y cube for some x and y in f. since F has at least three elements, we can choose an element in F that is different from both the zero element and the unity. This of course we can choose, that's the hypothesis. Now if we choose as x 1 and as y a, then let's see what happens to this condition. 1 plus a whole cube. Let us calculate this cube. Here also we can use our usual binomial theorem. In any commutative ring, the ordinary binomial theorem is valid and any field is a commutative ring. So this just becomes 1 cube plus 3 times 1 times a square plus 3 times 1 square times a. Now I think, okay, well, it does not matter if I write it like this, but still let's maintain the order. 1 times a square plus a cube, and that equals 1 plus 3a plus 3a square plus a cube. Now let us forcefully suppose that this is in fact equal to 1 cube plus a cube, and then let's see what happens. Suppose that is, it is equal to 1 plus a cube, then this expression would be equal to 1 plus a cube, and then after cancelling like terms we will have this. But keep in mind that f has characteristic 2. Since f has characteristic 2, so 0 is equal to 3a plus 3a square minus 2a minus 2a square, because this minus 2a and minus 2a square both are 0 in this field. So that means we have a plus a square, or a times 1 plus a. But according to our choice, a is not equal to 0. Since a is not equal to 0, so you can cancel a from both sides, or more precisely you can multiply on both sides by the inverse of a under multiplication. That would give us 1 plus a equal to 0, or a equal to minus 1. But again, keeping in mind that f has characteristic 2, minus 1 is equal to 1. And this is a contradiction, because a is neither 0 nor 1. This is a contradiction. So our supposition is wrong. That means this supposition is wrong, i.e. this is actually not equal to this. So that's how we have found two elements x and y for which we have this condition, and they are 1 and a, and that completes the solution. So let me end this video here itself. Next Saturday we are going to go back to again algebra problems from Lee, and tomorrow we have our usual analysis update. So with that, see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Truth. Have a nice day.